So we are very happy to have Samir Mathur today from remotely Ohio, and he'll be telling us about the black hole information problem, I think.
Okay, thank you very much for the invitation to talk here. I'm sorry I couldn't be there in person, and so thanks for agreeing to listen to the talk in this format. Please do stop me and ask questions if the format allows, and I'd be happy to try to answer them. Let me just begin by thanking everybody, which must be the people who are mostly there in the room, who have contributed to the fuzzball program and its development, because all I'm going to talk about is to say what I think is the philosophical understanding we have obtained from all the hard work that people have done with fuzzballs, and what's wrong with what other people are trying to do right now, and also where we should be going from here. Okay. So let me see if I can move the slide. Okay. So I think the underlying problem with black holes is that the whole point is there is a state of tension between two opposing results. The first is the no-head theorems, which tells you that if you try to make a black hole, everything falls into the central singularity and it leaves a vacuum everywhere else, in particular around the horizon. On the other hand, Bekenstein in 1972 gave arguments that the entropy of the black hole should be given by the surface area measured in Planck units. So the second argument, the one by Bekenstein, suggests that somehow the degrees of freedom live at the surface, or at least somewhere there. And the first one says, well, there is nothing at the surface. So in fact, the entire story of black holes has been the tension between these. And so people, of course, got very confused. And it also led to a lot of mystical thinking. Could it be the degrees of freedom are both there and not there? Maybe in some way of thinking they are there, in some way of thinking they are not there. And so it just became very confusing. Of course, you could say, why would you like to answer that question? Do we really care about this question? If it gets too confusing, let's forget it. But we can't do that because the issue is brought into sharp focus by the Hawking information paradox. And Hawking found that if you have a vacuum at the horizon, there's no degrees of freedom actually there, then the vacuum produces entangled pairs, and the entanglement of the radiation with the black hole, with the remaining hole, just keeps monotonically rising. And then at the end of the evaporation, you have the information paradox. In a normal body, you don't have the vacuum at the surface. The degrees of freedom are actually there, and they radiate the data. And in that way, when the black hole is actually evaporated, when this object is actually evaporated away, this piece of coal, the entanglement of the radiation with what's left behind actually goes to zero. So in fact, the whole issue of whether there is something at the horizon or not at the horizon is not something you can evade. It's actually right now underpinning the entire story of quantum unitarity. So you have to answer that question. So here's the question: is there data about the state or no data at the horizon? Do you have a picture like this? Is the whole thing like a normal body? And as I was saying before, because people could not understand which of these two was the answer, the no-head theorems looked absolutely solid, and then the area theorem looked solid, and the Hawking puzzle was standing in between. It led to confused thinking, saying maybe there is complementarity, which means in some way of looking you have the vacuum, in some way of looking you have degrees of freedom, or you have holography. The degrees of freedom are there, but you could think of them as being on the surface. But actually, all these words were just an attempt to like have your cake and eat it too, and they were not actually trying to understand what's really happening with the black hole. But actually, with the developments in string theory, which came from D-branes and non-perturbative string theory, the answer to the puzzle actually soon became clear. And so what you have to do is you have to just make a black hole with the objects you have in string theory. And this is the green things here are the D5 branes, and the red lines here are the D1 branes, and you can put momentum excitations on them. And with this D1, D5P bound state, you could make lots of states, which is what Strominger and Waffer did in 1996, following the earlier work of Sen in 95. So if you just make an indirect argument following them on this particular bound state of D1, D5, and P charges, then you compute the entropy of that, and you find that the entropy of that computed by these index arguments is actually equal to the surface area. So this tells you that you actually are on the right path in trying to describe a black hole by the degrees of freedom you have in string theory. But of course, to resolve the information paradox, it doesn't help to count the states. You need to know what the states look like, and do they have the data at the horizon or not? And then if you try to estimate the size of a bound state made by D1, D5, and P charges, it was found that In fact, it's not that all the mass shrinks to a Planck-sized object in the center, leaving a vacuum elsewhere. The size of the bound state actually appears to grow with the number of charges, n1, n5, np for the d1, d5, and p charges. It actually also grows with the string coupling, and all in such a way that the size of the object is always of order the horizon radius. So once one encounters something like that in string theory, the picture of course changes, and what one must do then is to do a proper job and actually make out all the bound states one by one and see whether they have a vacuum at the surface or there's actually data there. And so one actually tries to make them. In every case that one has actually tried to make the bound state and succeeded, one finds you actually get this. It looks like a piece of coal and you don't get a vacuum horizon. So that's the whole fuzzball game in which I believe almost all of you there in the audience have been working in one way or another. So we've actually answered the question, is the data on the horizon, or is the horizon the vacuum that we expect in the semi-classical picture? And the answer is there is data on the horizon, and the state there is nowhere close to the vacuum. Like in the traditional picture, the overlap of that with the vacuum was like almost 1 up to some small quantum gravity correction of order epsilon. But in the actual situation, the vacuum is like negligible there. It's just something completely different. It's like just like a piece of coal. And so in fact, what happened is that if you look at all the possible space of D1, D5, P bound states, it's easiest to start with various corners of the space. So you try to go to something extreme in one way or the other. You could either have, let's say, 0 momentum charge and you get 2 charge states, or you could take that and just 1 unit of momentum, or put lots of momentum but the same on all the strands. You could make various kinds of special cases, and in each of those cases you're actually able to construct the corresponding gravity solution, and it doesn't look like the traditional hole. It has always come out to be a fuzzball. So you would think this basically settles the issue, but then people were still not comfortable with this, at least in the early years of fuzzballs, and they asked, could it be that the other states, the ones in the middle of the diagram, maybe they have a smooth horizon, and only the extreme cases which one worked with in the beginning, maybe they are the ones which are fuzzballs. It's a strange thing to say, because you are trying to solve a problem and you have found like all these cases and it's pointing to a clear solution. So why would one still be stressing the fact that maybe the other states that you forgot should be actual traditional black holes with a horizon? Because the problem is, if the other states did have a horizon, then how would you resolve the information paradox? What were these people trying to say? And what they were trying to say was that perhaps the horizon is there, but the small subtle quantum gravity effects that we can always have might be solving the problem. And this issue started with Maldaceno's paper in 2000 and was picked up again in a slightly different guise by Hawking in 2004, and had led to a lot of confusion in the field. Because the idea was that the number of particles emitted by the black hole is of course very large. It's of order the entropy of the black hole. So n, the number of particles emitted by the time you evaporate the black hole, is a very large number. So even if the correction to each pair epsilon is very small, perhaps the overall effect of this on the entanglement might be such that the page curve actually comes down to 0 by the end of the evaporation process. But in fact, using these strong subadditivity theorems of quantum entanglement entropy, what can prove that's not the case? If the corrections are small at each step of evaporation, it doesn't matter how large the total number of emitted quanta is, the entanglement at step n plus 1 is always more than the entanglement of step n by the amount of the leading order entanglement that Hawking computed. In the simple model, it's log 2, and the corrections can only reduce it by at most 2 epsilon. So in fact, if the exact curve that Hawking found is the black line here, with all the small corrections, it would actually just be the dashed line. You wouldn't have solved the problem because the entanglement still keeps rising. So no small correction to the semi-classical picture can alter Hawking's conclusion. And so we have to get a large change, and that's what the fuzzball calculation was showing us. So now we can fill in the middle of this diagram as well. Around the edges, we already had these constructions, but in the middle, you can say, well, if there were black holes and if there were not fuzzballs, then you would have to have, you can now make it very precise, one of the following 3 things must happen. Either you have a loss of unitarity in your underlying quantum gravity theory, or you're left with remnants, which as we know have their own problems, or you would have a violation of low energy dynamics at infinity, like in the lab. So assuming that you don't want any of these 3, the small correction theorem says that all these guys in the middle, because these are not extremal, they all radiate. And once they radiate, you're actually going to have, you simply cannot solve the problem without running into one of these difficulties. So together with all the explicit cases which have been constructed, and the fact that in the middle, the small correction theorem tells you that there is no other comfortable resolution of the problem where you have a vacuum horizon to any good accuracy, one would say that the problem is solved. So the information paradox is over. And because we have been doing fuzzballs for so many years, it has been over for more than 2 decades. And it's very surprising that some people still keep saying, we do not quite know the resolution of the information paradox, but look, we are making such exciting progress. One day we have islands, we have wormholes, we have QES, we're having so many new ideas. What are these people trying to do? And the point is, as I've been explaining, these people are looking for solutions to the paradox in a direction which has already been ruled out. And where does their error come from then? And the error comes from an incorrect understanding of what holography can and cannot do. The specific errors in different models, that is in these approaches involving wormhole, island, QES, non-locality, and all these words like ER equals EPR, well, they were actually analyzed in this paper from last November, and I will be just mentioning an outline of what we did over there. But in short, what happens is that each of the models that people have tried or been talking about over the last so many years, it either runs into non-unitarity of the underlying theory or unacceptable behavior of low energy physics at infinity. So why are people going in a direction which is having all these manifestly erroneous conclusions? Well, the error can be traced to 2 places, and the 2 places I have called here A and B. And it's very important to understand what these errors are, because a large number of people in the field actually do not quite know what they are doing wrong, but they simply keep doing calculations, and then it leads to these absurd answers. So the first problem is a philosophical error. What happened was that the entropy of black holes had suggested the idea of holography. We just saw that the entropy is proportional to the area. So the idea is somehow there must be something on the surface. And later, holography was noted in the form of ADS-CFT duality, which by itself is correct. It is very ironic that even though ADS-CFT duality was discovered by the same folks who were also thinking about black holes, these 2 situations are actually not the same. And so trying to make them the same, trying to say that whatever we have found with ADS-CFT duality also must apply to the black hole in some way, so that what's inside the black hole might be on the surface, or there might be something holographic, some other way of thinking about things. Trying to force that idea through is at the root of the errors which are encoded in all these ideas about wormholes and islands. We will see exactly what the error is, and we will see why one cannot possibly go down that path. But then if people are going far down that path, there must also be something that they're doing at the technical level. And the technical level also has a fundamental error. Almost all of the intuition guiding the ideas of holography and wormholes stems from using the semi-classical geometry of the eternal black hole, which again goes back to Maldaceno's paper of 2000. But this particular geometry, the eternal black hole, as I will show you, doesn't actually exist. So if you use a geometry which doesn't exist, all the conclusions you get from it are also erroneous. And it's the geometry doesn't exist in the same way that a traditional black hole doesn't exist. If you take the normal single-sided black hole and you say this guy exists and all the conclusions coming from it, I'm going to accept. Well, then you have the conclusion that the entanglement will keep rising. You will have information loss. And as Hawking said in 1975, you should replace the S matrix, which is unitary, by the non-unitary dollar matrix, and just say that in quantum gravity, unitarity is not violated. You only have density matrices and not wave functions. Now, we don't accept that conclusion. And to not accept that conclusion, we have had to find that this is not the correct picture of the black hole. You actually have fuzzballs instead. But exactly the same error when it's applied to the eternal black hole, where you use that geometry, you come across all these ideas that there must be wormholes and this entanglement generates spacetime, and you have ER equals EPR. They all follow from the same error applied to the eternal black hole. So these 2 errors have been guiding this opposition to the fact that fuzzballs have already resolved the puzzle. And in the end, I will come back and tell you why it is important to understand what lessons we have gotten from fuzzballs in order to make progress further in the directions of quantum gravity and in particular cosmology. Okay, so let's start by thinking, what is holography? Where does it work? And where does it fail? So really, holography goes back to what's called open-closed duality in string theory. So if you have 2 D branes, as I have drawn here, you can stretch an open string between them, and you could have a one-loop diagram of open strings, which looks like this tube. Well, you could also look at this diagram in the cross channel, where it looks like a closed string propagated from here to here. So it's a tree-level diagram of a closed string. And because you can think of the same wordsheet in 2 different ways, as a one loop of an open string or a closed string, a tree-level closed string, this is what we call open-closed duality. Now, suppose this has been known for a long time, but suppose you had a large number of D branes, then in fact, if you look at these open strings, the one I have drawn here, it could either be in the ground state of the open string, or it could be in any of the excited states where there are oscillators on the string. But if you have a large number of these D branes, then there's more phase space for taking an open string in the excited state and breaking into open strings which are in the ground state, because each particular open string has a Chan pattern factor from the two sides, which are n square possibilities. And so if you take an open string, let's say in the third excited state, and you break it down into, let's say, 10 strings all in the ground state, then you get that many factors of n squared. So there's much more phase space for having open strings. And so if you actually take a state, and if the coupling of G, the string coupling, which allows you to break and join open strings, is not too small, then in fact, any open string you put in the excited state will quickly break into and spread over the phase space of open strings in the ground state. And the open strings in the ground state, well, their interactions are very simple. It's been computed a long time ago also in the early days of D branes. They're just given by the Yang-Mills actions. You can think of them as gluons and the interaction of the Yang-Mills actions. Okay, so if the overall energy of the state is low, that is, you don't excite the open strings into higher levels, n is large, so the open string that you have at higher levels want to break into ones in the ground state. The string coupling G is not too small, so G times n is big enough so that you can actually break the ground state. Then you can basically say that all the effects of closed strings and open strings, which could have been excited in arbitrary levels, can just be written down in terms of Yang-Mills. So that's the observation of ADS-CFT duality, and it's just a straightforward observation, and there is nothing wrong with it. And in practice, it looks like this. If you have some D branes here, and you send a closed string which falls on it, the closed string will break into lots of little open strings and make some excitation of these D branes. As excitation will then spread, these open strings will then spread and maybe become more numerous. High energy open string can break into two low energy open strings and so on, and it just keeps spreading in some complicated way described by the super Yang-Mills action. In the closed string dual picture, it actually looks much simpler because the string which is coming, it actually just falls into ADS geometry throat, and so it just keeps going in and in. As the disturbance spreads wider and wider on the D branes, this thing just keeps going deeper and deeper in. So that's ADS-CFT duality. And you can see from here, the open string description is very messy because it is strongly coupled Yang-Mills with lots of gluons. But at least for this excitation, the closed string description is very simple. The string just keeps falling deeper and deeper into the ADS throat. And there's nothing wrong with this duality. It's completely correct. And they're just connected by open-closed duality. It's the same physics, just seen in two different variables. Now, what happened with the wormhole paradigm is that people then thought, okay, now that we have this, perhaps we have learned also something about black holes. Let's try to become a little inventive in what we can do. So here's the picture again of what we saw with open-closed duality, with ADS-CFT duality with D branes. Now, what's the situation with black holes? So they said perhaps this idea, so the intuition running at the back of the mind with these people was the following, that here there's one description of the same physics, the open string description, which is extremely messy because nobody can write down a million open strings in strongly coupled super Yang-Mills. So suppose the exact quantum gravity theory gives you a very messy state of black holes here, and that's emitting just like a piece of coal. Now, we don't know what the state is, but let's not worry about it. Suppose it's actually like this, then perhaps in some complicated set of variables, with the way we extract these closed string variables here, the whole thing actually looks quite simple. Now, it can't look simple for all possible questions, but at least for a code subspace, what the word uses, the code subspace, for some simple subspace of all possible states in here, we can basically use semi-classical low energy physics, and in that everything would look just like Hawking thought. Well, if semi-classical physics can be extracted in this way, so this picture would be like this picture, and this picture, the messy picture, would be like this picture. So if physics could look like this, then what have we learned about the Hawking puzzle? Well, Hawking had used this picture, and he was getting the pairs, so you can get them. But this is some kind of an approximation. Now here the duality was exact. Now here they said, okay, maybe it's somewhat approximate. And that's where the idea came that you would have small corrections here. And the small corrections basically would make this also unitary. But otherwise, this would be a good approximation to what's going on here if you focus on low energy physics. Now, it turns out that this is not true. As we will show that, in fact, as we will indicate later, that the code subspace extraction from this is actually not possible. And there are very fundamental reasons as to why this is not possible. But this is the intuition which is underlying all the opposition to fuzzballs from like the last 25 years. So the intuition here, just to emphasize again, is that if you have some medium, let's say like a piece of wood, and you just want to see, so its actual atoms and all are very complicated and everything is very complex in it. And then if you just want to say, okay, I hit the wood and I excite sound waves in it, then you're just looking at some low energy collective behavior and don't actually care about the details of where the atoms are. And that could be described by some continuous medium with, it just looks like the, some medium like a vacuum. And that would be like this kind of picture. As we'll see that you actually cannot do that and extract the information of the Hawking radiation. That analogy does not apply to black holes. But because it looks so persuasive, this mess has been going on and still continues to go on today. So there are many different versions of what is happening to the entanglement in this wormhole paradigm. And a systematic study, as I said, of each of them runs into a contradiction. And we analyzed in this paper from last November. Let's actually just take it more concretely and see what we can and cannot do when we try to extract a low energy subspace out of a complicated quantum gravity system. So what do the entanglement issues do when you're actually trying to extract a low energy subspace? So the following is what one can prove, and it is proved in that particular paper I mentioned. But let me state the result, and then maybe it will appear immediately intuitive to you. Suppose you follow along with what these people are saying and assume that the exact description of the black hole is something very complicated, string dynamics. And let's say this is exact quantum gravity. In some region, we'll take it all the way up to R equals 4m to include the black hole and its surrounding. And all this evolution we'll assume is unitary. So this is the exact description. And we have not assumed that there is anything close to semi-classical here. It's a complete mess. Now, far from the hole, let's say you go 100m and outside, we'll say the exact dynamics is given by just normal string theory around flat space-time. So just what you would open up a book like Green, Schwartz, and Witten or Polchinski about string theory in flat space. There are gravitons, there are strings, and you know all those interactions. There's nothing novel happening here. Now, from the exact degrees of freedom, which I have called G exact, you can extract in this region, which are less than 4m, some effective code subspace. Let's do what these people want you to do. You define some effective variables, which are some complicated functions of the exact degrees of freedom. They're not telling you how to get them, so we are not telling you either, but this is anything that you want, some effective degrees of freedom have been extracted. Well, once you do that, the exact Lagrangian of string theory, whatever it is, again, we may not know how to write it, will give you some effective Lagrangian of these effective degrees of freedom. Now, at this point, note there is no choice. If you define some map from the exact degrees of freedom to some G effective, the dynamics of the exact degrees of freedom tell you what the effective degrees of freedom will be doing. I emphasize that because a set of papers out of the ones that people have been writing in the last 2 years, in fact, break this link. They keep giving an arbitrary dynamic that they want the effective degrees of freedom, which doesn't actually follow from any exact dynamics, and in fact, cannot follow from an exact dynamic. So these are the kind of mistakes that people have been making. So I'm just stating some very elementary facts. Also, any quantity you want to compute in the exact theory will map to a corresponding quantity in terms of effective variables. It's just a map of variables. And again, not following this map has also led to errors in several of the papers in the last few years. So anyway, if you do all that, what these people would be saying is some complicated mess of degrees of freedom here, some complicated messy degrees of freedom here. Well, they become this code subspace, and which then satisfies to some approximation a scalar field equation, let's say box phi equals 0, which you can then put into oscillators. And then, of course, you can't stop getting these creations of entangled pairs. But we don't ask for too much from these entangled pairs. We ask for very little in this particular wormhole paradigm. So we will get this entanglement thing because the box phi equals 0 to some approximation does mean the entanglement pairs will get created at the horizon. And you can model the entanglement like this. But we ask for very little from these entangled pairs. This effective field theory, we only want to work for low energy modes, say wavelengths bigger than 1 Fermi, the ones we see in the lab. And we're not trying to extend to the Planck scale or anything. And the dynamics we are extracting for these modes doesn't have to be exact. It's only there after some approximation with errors epsilon, which of course must be much less than 1. We don't even assume that this map we are making should work for all time. It just works over some time to emit, let's say, 10 or 100 Hawking quanta. And then maybe you have to make a new map to get the semi-classical description. Even with all this, you could say, okay, I have gotten some semi-classical code space over there. And so this will be the situation at the end of these assumptions, that here's the exact guy, and you've pulled some mess out of it. And that's the thing which will go to infinity as the radiated stuff. But then in this code subspace description, these new variables, it looks like a pair of entangled low energy quanta. Well, then when this goes to infinity, because at infinity, you just have ordinary gravitons and strings. And because you're at low energy, it basically becomes some bunch of gravitons. And in this approximate code subspace that you extracted, it will also become gravitons. And again, these will be only approximately the same because this was an approximate up to some order epsilon. Okay, so we've done everything that these people wanted us to do. At this point, the effective small correction theorem, which is a small extension of the old small correction theorem, tells us, and was proved in this paper, it tells us the following. With all these assumptions, the entanglement graph of the exact quantum gravity theory, which is the one for which you're trying to solve the information paradox, will actually keep rising. So in fact, if you wanted the exact quantum gravity theory to have a unitary page curve which comes down, and then if it has an approximate description which looks like the Hawking one for pairs, even for a few pairs, 4 or 5 pairs at a time, and then you change the description and it's only approximate, all that, you still can't do it. The exact theory actually cannot be unitary. I put that conclusion all on this slide. So everything I've said in the last 4 or 5 slides, it's also, the conclusion is summarized in this slide. The following belief, which is the underlying belief of all these people who are opposed to fuzzballs, is actually false and proved in that theorem, the effective small correction theorem. Suppose the exact thing is actually unitary and radiates like a piece of coal and the page curve comes down. Suppose that were true. Then in some code subspace, if you start looking for semi-classical dynamics with all those approximations and all the leeway we have given them, you actually cannot get this. So in fact, the underlying belief that these people are trying to get that the exact dynamics can be modeled at low energies like effectively empty space with small correction is actually not possible. And if it is not possible, why have they not realized it by now? They certainly have been told about it multiple times, but the point is this proof is not intuitive. And the reason is it uses the strong similarity quantum property of entanglement entropy, and that has no intuitive proof. So it does take a little bit of thinking. On the other hand, if you go back to how all this happened, you can see where the guts of the theorem is coming from. If you take the exact theory and you take a bunch of stuff from it and put it out here, okay, and what is here then goes to infinity. At infinity, everything is just the same. It's just some degrees of freedom, so it's just going to become gravitons. If you pull something out from some mess, then the entanglement of that mess just goes up. So if you could actually write as 2 different things which look like semi-classical quanta, then the entanglement of this guy with what is left behind has clearly gone up in this picture, which means it has gone up to some order epsilon in this picture. Okay. So in fact, if you make the entropy go up in the semi-classical, the way it does in Hawking's calculation, and this is any approximate to the exact one, then when the entanglement of infinity and the whole went up in this picture, up to order epsilon also goes up in this picture. Now you could say that because the small order epsilon, suppose epsilon is 0.01, by the time you emit 100 quanta, all the errors could accumulate, and then it could become an order 1 change here. That's what was the belief in the old belief in small corrections. But that's where you need the strong subadditivity, and you can prove that this actually doesn't happen. It actually cannot happen. So in fact, you cannot actually accumulate the small errors you have between these 2 pictures and say that in this picture, the page curve comes down. In this picture, look, Hawking found going up, but that was his problem. He forgot the small errors. So what these people are doing they are still being confused by the fact that they're trying to maintain a smooth horizon, and then they are saying that the small corrections in one way or the other actually allow them to have a unitary theory. And so in fact, you can't do that. And so the basic belief in the direction which they're going doesn't work. So why did this attempt, let's now try to see if we can make sense of this answer that you cannot do this in some intuitive way. Why was this attempt to extend the ideas of ADS-CFT to Hawking radiation go wrong? So let's go back to this picture. The idea of ADS-CFT was you have some d branes here, and you can either excite these and make them into, if you excite these, you get a mess of open strings, and you excite this, you just get a string falling in ADS space. And these 2 are exactly equivalent, just a change of variables. And the reason this worked was that these d branes, you started with them in the ground state, and you just take d3 branes, they are a unique state. So you have a unique state over here in this blue circle. The correspondent dual theory is also in a unique state. It's just the ADS vacuum. Okay. If you excite this in a certain way, there's a corresponding excitation over here. So it's always one state going to one state. Now, if you come to the black hole, the situation is actually quite different. Here you have many different microstates because you have the entropy of the black hole. And in fact, what you're looking for is that the radiation should carry away information about that state. So if you replace all the states in some approximation by the vacuum, well, the vacuum is just one state. So the moment you replace all this mess by one state, the vacuum, you're going to lose the information. So in fact, whatever you try to do with these guys, it'll never actually end up getting you the information back. So what these people have been saying is, okay, in this semi-classical approximation, we don't want the information back. And in this exact theory, we want it back. And then we are happy with that because this was an approximation and this was exact. The information comes out, page curve comes down, and the approximate stays like this. Look, everybody was right. We can go on with semi-classical gravity the way Hawking did, and everything is actually also unitary, but that's exactly what is not possible. This cannot be an approximation to this, and for that, you really need the strong subadditivity to understand that the small epsilon errors cannot accumulate to turn the page curve, which is going up in the in the effective theory, the page curve is obviously going up. That's back to the old Hawking theory. Then the exact theory, the page curve will also go up. The errors cannot accumulate to actually make it come down. So I know I've said this in a few different slides, but it's very important that this error is basically still running through the entire thinking of a large part of the community and is causing the field to just get blocked without actually understanding that the problem has been solved. You can see what I just said even more explicitly with what we know about fuzzballs. So here is let's say you can make the two-charge extremal fuzzballs where we can all know how to make them exactly. So here's the dual CFT. If you probe the dual CFT at high energy, just make a high energy excitation, then here are some high energy quanta in the CFT. And this kind of excitation, we know how to map it to an excitation which in the gravity theory, it will be something, a high energy excitation high up in the throat, away from all this cap region. And at high energy, these guys are basically all the same. There's no difference between the different vector states of two charge. And so they can actually be mapped to the same geometry. The geometry corresponding dynamics here in the throat, it's also the same for all the two charge geometries. You see the universality. But exactly at this, when you go to low energies, you start seeing the effects of how these different strings, now in the two charge geometry, so this is the D1, D5 system, and they have different multi-windings. Suppose this guy is joined to this, or maybe this guy is joined to this, the different winding sectors. Well, that difference starts showing up once you go to low energies. But at those low energies, this infalling quanta has now reached the place where all the different states are actually different. And so you can now see when you start seeing the differences in the CFT, you also start seeing the differences in gravity. In fact, this happens exactly at the place where the entropy is given by the surface area. At this point, you cannot replace them all by one state, because if you do, you're obviously making a mistake and you cannot reproduce the dynamics. So here is the basic lesson. The idea of holography, you cannot apply that to surfaces like the surface of a black hole, which is actually defined. Where did the surface come from? It's actually the surface whose area gives the entropy contained inside. So it's the large entropy of the black hole, and the fact that surface area of the black hole actually tells you how much entropy is inside. And it's not zero because the surface is there. In any situation with entropy, you cannot use holography. And so this is where the whole thing is very ironical, how people got misled. The whole idea of the black hole surface being proportional to the area kept bringing this word holography all the way, for about 30 years, starting with the, with the works of Susskind and all these things. But ironically, even though we have found holography somewhere in string theory, you cannot apply holography to understand Hawking radiation from the surface of a black hole for the very simple reason that I have given you here, supplemented by the small correction theorem, which tells you that it actually just cannot be made to work. So in fact, not understanding the fact that you can't apply it to Hawking radiation, it looks very persuasive because here's the black hole. We wanted holography. Look, now we know holography. Why can't we use it? But in fact, you can't. Okay, so now that you can see that it doesn't make sense to replace many geometries by one geometry, like I was saying here, why would you replace many geometries by one? Of course, then you're going to lose information and it's not going to work. Why were people trying to do this? And the error actually got the whole circle of ideas they have. They came from this one technical flaw I talked about at the beginning of the talk. It comes from an incorrect belief that entanglement can actually generate a space-time connection. And this goes back to an old paper of Maldacena, which was followed up by some work of Van Damsdonk. It was further developed into the wormhole paradigm by Maldacena and Susskind later on in 2013. But this entire chain of ideas is actually incorrect and is governing a lot of thinking in the wormhole community. And I want to show you what exactly is the error there. So if you consider the eternal black hole in ADS space, so just take this one. So it has 4 quadrants. This is the normal space, like this is the space-time infinity outside the hole. This is the region inside the horizon, but the eternal hole also continues. So it has future singularity, a past singularity, and other stuff in here. But if you slice it across the middle, you see this thing called the Einstein-Rosen bridge. So the two sides actually are connected by the Einstein-Rosen bridge. If you look at this eternal black hole in ADS, the space-time actually has 2 boundaries, one on the right and one on the left. And these 2 copies of the CFT, well, they are non-interacting. But they can be in an entangled state, but they're not interacting because these 2 places are physically separated. So people said that, okay, if this is take the eternal black hole here, its boundary is two non-interacting things over here, but they can be entangled. So if this is the dual of this, then entanglement between two things which are not physically connected, not interacting anyway, can somehow generate a physical connection between them, because look, here you see the Einstein-Rosen bridge. So this gave rise to an idea that entanglement can somehow generate a physical connection, and that looks like a wormhole, and that may somehow again say something about the information paradox. But we'll see that there's an underlying error in this argument. And that error was pointed out in this older paper here from 2014. There were several errors you can point out. I'll just mention one of them, and that's the following. Take each side of this eternal black hole and connect the outside regions to, let's say, flat space, just to connect it to a bath in flat space from which we can throw things and take things out. So it's just a convenience. And so from here, suppose you throw a particle into the CFT on the right. So when I just draw the blue lines, I just look at the picture where I have CFTs. And so each CFT is now connected to a flat space region. And when I draw the entire inside, I still have the same outside, but now I've replaced it by the actual gravity. So this is the CFT description, and this is the gravity description. Well, if I take two states which may be entangled, and in fact, let's take them to be entangled in the thermophile double state that Johan Malsina keeps talking about, let's take that state. Then if we actually throw a particle P on the right into this particular entangled state, then the information of that cannot actually come to the left. It's going to simply radiate back onto the right. That's because they're not interacting, so they expect the information to come back to the right. But if you look at the gravity picture, this one soon crosses the middle half. Well, as long as the information doesn't come out, it wouldn't have mattered, because it cannot physically come here, because the light cone structure, it will go into the singularity. But in fact, you can let the black hole evaporate. Just because the black hole is eternal does not mean it doesn't evaporate. Whenever you have horizons like this, they always have pair creation, in fact, on both horizons in this case, and the black holes on both sides actually keep shrinking. The only reason we call it the eternal hole is that we sometimes imagine putting reflecting boundary conditions where the radiation is fed back into the hole, or you can take the radiation coming out, take it out, and feed equivalent amount of energy in some other way to maintain the hole. That's why we call it the eternal hole, but otherwise the hole does evaporate. And since everybody's assuming that everything is unitary in black hole evaporation, then in fact, when you allow the hole to disappear, the information has to come out either on this side or this side. But it's impossible in this situation of gravity to make sure that the information comes out only on the right. Firstly, it's already crossed over to the left, so it's more likely it comes out on the left than on the right. But even more generally, you can send two particles, one from the right, one from the left, make them collide in this future wedge and break into three particles. Now their information, let's say, of their spin is completely shuffled between these multiple particles, and it's impossible to imagine that the information on the right of the right particle comes only on the right and the left comes only on the left. You can make other paradoxes like this, and you find that in fact, this two entangled but non-interacting CFTs cannot be the dual to this eternal black hole. So there is something actually more basically wrong with the whole idea that entanglement can generate a physical connection. This is something that every student of quantum mechanics would have told you right in undergraduate courses. And so let's just go back to this, and it's a question that you could ask to anybody who's talking about entanglement generating space-time, because the question is so very basic. So let's take some object here, a piece of coal, a star, a planet, a black hole, whatever you like, and let it be in some state called psi I. And with that, I will take an electron, let's say with a spin state S, which could be plus or minus, let's say, and scatter it off it. So I start with S tensor psi I. I hit this thing here, and what will happen? The spin can change. It will go to some other spin state S prime alpha. And instead of this guy can change psi I alpha with some weights d alpha. Okay, so this is just a general scattering of an electron off a piece of coal. And suppose I have another piece of coal far away, entangled. I'll entangle it later, right now in a tensor product state in some state chi I. This guy's not doing anything, so the entire state is, the whole dynamics is just here. Okay, so we know what happens here, but now suppose I have entanglement. So instead of taking state psi I for this, I take Ci times psi I tensor chi I. So I take psi 1 tensor chi 1 plus psi 2 tensor chi 2. I just weight them in different ways. Do we know what happens in this case? Well, of course we do. The linearity of quantum mechanics tells me that if I know how to scatter a spin of psi I tensor chi I know exactly what will happen if I scatter the spin of psi I tensor chi I, weighted with Ci, and then summed over I. It's just given by simple linear superposition. Well, everybody knows this. So entanglement actually cannot do anything for you. If we have now made these, let's say, two charge fuzzballs. They're just like pieces of coal. You can just see that, just some local structure here, just some other local structure here. You entangle it, you simply get a linear superposition of local structures. So what are people trying to talk so much about entanglement and say it does something, it makes wormholes, it makes physical connections, they could be traversable, and I can get some information paradox out of it. All of it is in stark contrast to what you are forced to have with the linearity of quantum theory. So what are people trying to do here? As we said, entanglement cannot do anything in quantum mechanics. It's a well-known fact right from undergraduate days, because if you understand the dynamics of all unentangled states, the linear superposition tells you everything about dynamics of entangled states, and nothing new happens. Nothing interesting can happen, because simply a linear superposition of what happened in the individual cases. So how did we get into the mess of things like ER equals EPR? Well, so what happened was, if we start with the dual to two entangled CFTs, what do we actually expect from what we know about black holes today? Well, each CFT state is just dual to a fuzzball, which is just something with a cap. It's a messy cap. It's there. And this guy is dual to its own fuzzball. So if I have one CFT in this room and you have one CFT all the way there in Paris, each one is just a fuzzball. And if you entangle them, you have two entangled pieces of coal or two entangled fuzzballs in two distinct places. Why would someone say that the two different fuzzballs are now connected by a throat, and it becomes more like an Einstein-Rosen bridge between them? How did people come into this conclusion, which, as I'm going to tell you, is incorrect? It came by asking the reverse question. You start with the eternal hole, like this diagram, and ask, what is the dual to this geometry? And if you start asking the question that way, of course, this guy has two boundaries, one here and one here, and the two boundaries are obviously not connected. And then, as we said, that leads to a circle of arguments that two disconnected things, but entangled, should, in some other description, lead to a connection. Okay, so what's wrong with this reasoning? And what's wrong is that this particular space-time doesn't exist. But why doesn't it exist? Well, you can go back and ask the same question about the old single-sided black hole. We have found doesn't exist. It actually becomes fuzzballs. So you really got to ask why this space-time doesn't exist, because if this one did, you get to the erroneous conclusion that the quantum gravity doesn't actually preserve the unitarity of the S matrix. The small correction theorem tells you that anything close to this also won't help. You will really have to lose unitarity. So in fact, you have to realize that this solution doesn't exist and is completely modified. And so for the same reason, this guy doesn't exist. And the only thing which exists is actually this. So this guy gets destabilized into this by fuzzball corrections. And if one doesn't understand that, like if one hasn't accepted that black holes are really fuzzballs, then one doesn't even know how to solve the information puzzle at this language. And then so one keeps getting forced, one keeps accepting this diagram and keeps getting to this idea. And then all these ideas about space-time being built by entanglement keep going back to them, and then they keep getting confused. Okay, so the real question is, why does this geometry not exist? It was semi-classically looking fine, just like this guy looks fine, so why doesn't it exist? And so I mentioned this in earlier talks before, so I just mentioned this briefly again. And then I just mentioned it because when I come to a later stage, I will need a little bit of input from here. So why the semi-classical approximation violated? Semi-classically, it would seem the shell just keeps going in, and once the shell goes inside its own horizon, the light cones turn inwards, and you get a semi-classical evolution. Well, how did the whole thing turn into a fuzzball? Well, the answer is you can actually find there's a tunneling path from the shell configuration to the fuzzball configuration. And the tunneling amplitude is actually very small, as you expect for a massive object tunneling into another massive object. But the smallness of the tunneling amplitude is offset by the large number of states that you can tunnel to. And here the estimates that if you compute the property of tunneling is the amplitude of tunneling mod square. So there's some action for tunneling. And so it'll be like e to the minus twice the action for tunneling. If you set all length scales to be order the horizon radius, you find that this action computed from the Einstein action, all dimensions, just comes out to be the horizon radius upon L Planck to the power space-time dimension d minus 2. So suppression is in power of exponential of minus RH over L Planck to some power. So the probability of tunneling to any individual fuzzball is indeed very small. But the number of fuzzballs given by the Beckstein entropy, and if you put that in, you find the same number RH over L Planck coming in. So in fact, if you look at the tunneling probability being small, and the number of possible states to which you're tunneling being large, you can imagine that there might be an offset. And so in fact, the semi-classical picture of the whole, which says that you must use just the classical action, it doesn't have to be correct. The measured term, which comes from the number of terms which are contributing to the path integral, is in fact compensating the suppression of the classical action. And this is what we call entropy-enhanced tunneling. And this then doesn't allow the semi-classical dynamics to be valid. An indirect argument indicates that the exponentials actually cancel. But the more concrete things which I have seen here are papers by these people who actually made specific examples of this entropy-enhanced tunneling in a family of fuzzball states. So a quantum mechanical analogy could be that if you have a particle in a box with a small amplitude for tunneling into other boxes, the amplitude could be small, with the number of other boxes are like these other states, the fuzzball states. This is the shell state, these are the fuzzball states. Even though you have a small amplitude tunnel into any one particular state, if there are many states you can access, then in fact, it will tunnel out in a very short time and become a linear combination of what's in all these other boxes. So that's how the semi-classical approximation breaks down. And in fact, we know that this state, from the simple example of the two-charge hole, which has been solved completely, we actually see the reasons why this state doesn't actually arise in the full quantum gravity theory. All the states are just linear combinations of objects like this. Well, the same effects will destabilize this geometry and actually basically leave you with this geometry. But if you don't realize that and you keep this geometry, then you will see the Einstein-Rosen bridge, the ER equals EPR, and this picture here, which I took from the paper of Maltzner and Susskind in 2013, saying that, okay, so then there's entanglement from here to here. Now, this is entanglement not in the CFT, whose dual was in the gravity. These guys took it one step further, and they said, just within the gravity theory, if something is entangled with something, there will be a wormhole between them. There is absolutely no reason for that. That's not even this setup, because here you had the entanglement was in the CFT and the wormhole was in the gravity. But here they were saying entanglement in gravity is another wormhole in gravity, but actually none of these things are true. Okay, so then at the end of this, if nothing that they're saying is working in this fashion, concretely, what are the papers about? What are people trying to say? So as we have seen, the story actually ended here. We knew that this thing will, early estimates said they should look like fuzzballs. I just put this thing down here because this came before any ADS-CFT came in the story. You can just look at the D1, D5P bound states of Strominger and Waffa, estimate the size, and you can see that they're just going to give you fuzzballs. And later when people have computed these, which is essentially all the work that you guys have been doing, you find, yes, they are fuzzballs. Story is over. Okay, I'm going to come and talk about what I've recently been doing about the vector structure with fuzzballs. But this is the direction I think that physics should actually be going in. Well, this ADS-CFT of Maltzner was actually correct, but all the other things that have been said about black holes from it are actually false, because the small correction theorem actually rules all of this out. So in fact, what are they trying to say? So right now, what the papers seem to be saying is the following. It's a two-step argument, step A and step B. Step A is a central dogma, which they call it the central dogma. It says that as you assume the exact quantum gravity theory, in that theory, the black hole radiates like a piece of coal and the page curve comes down. Well, just stop here for a second and you should ask the people, why are you saying that? Because showing that this happens was exactly the puzzle. The no-head theorems had told you there's a vacuum at the horizon, and then the entanglement keeps going up. The small correction theorem told you the small corrections can't fix that. So you have to break the no-head theorem. For that, you have to work with the actual full quantum gravity theory. If you just look at 2D gravity models, which they talk about these days, there is no hair there. They don't even make any hair there. They're not changing the state of the horizon. So what are they trying to do? Well, they keep saying that this is an effective theory, and so it has the vacuum horizon, but somehow in the exact theory, the page curve will come down. But that's begging the question, because showing how it can come down in the exact theory was the question. But that's the question the fuzzball people have solved by actually showing what structures in the exact quantum gravity theory allow those states to be there at the horizon. But in fact, there is no statement here. This is equal to assuming the answer, so you're not even addressing the information question. So then what are they trying to do? What they were trying to say was, okay, if somebody comes and shows us that the black hole is like a piece of coal, so maybe they can say to the fuzzball people, thanks, you've done that now. Then they're saying, well, from that we can extract a semi-classical code subspace. So for most purposes in life, because we are at low energies, we should use this description. So in fact, all this fuzzballs that people have found are actually useless, because whoever wants the detail, those details, if you found them, keep them. They're not of any use. We're really going to use this all the time. Because this is the description of the exact theory, there's no unitarity problem here, and we are exactly back to what we were doing. But in fact, we have shown that B is actually false. So neither of the beliefs A and B make any sense. A is equal to assuming the question, and B in fact can't be true. So what is there in these papers over the last 2 years? So we spent quite some time trying to analyze about 50 different papers, and then we extracted something from essence from some of those papers, trying to put it together in this long paper from last November. And actually they're not doing the same thing, which is why it's actually so confusing. Different papers are saying completely different things. I'll just try to mention to you in outline what a few of those papers said. So some of them said the effective degrees of freedom, you make them out of the exact degrees of freedom, but don't make them from the regions in the whole. You make them from the degrees of freedom around the whole, at let's say up to 4m, and also degrees of freedom from infinity. And this more complicated way of defining effective variables, somehow it'll give me a smooth horizon. But actually it doesn't work, because if you make degrees of freedom that way, you can show that doing ordinary experiments at infinity, low energy experiments, will modify the observations of what you will scatter or not scatter from the black hole near the black hole. And that even those people do not find acceptable. But you can show, we show in our paper that this will automatically happen if you define variables in this fashion. You can try to say that the degrees of freedom at infinity are not independent of the degrees of freedom in the whole. Okay? So this has been, a lot of this has been mentioned by many people. What you're treating as independent degrees of freedom are not independent. But if you do that and you follow to its logical conclusion, we show that in that case, low energy experiments at infinity will disagree with experiments in the lab. You can also say, some people said the spacetime inside the hole, it pinches off into baby universes. This is the work by Morolf and company. And then there'll be symmetry between multiple baby universes and will change some dynamics at infinity. But if you do that, if you look at it more carefully, we actually showed the evolution of the black hole interior will not be unitary. They've also argued the page curve can come down using replica saddle points and all that. But in fact, none of that is correct either. You cannot actually show that the page curve comes down by just playing with the same semi-classical gravity, which people have been playing all along. If you use 2D effective gravity, actually the page curve goes up. That was known in the old papers of the CGHS model and the RST model and so on. So what they have done is they've actually looked at a quantity which is actually not the entanglement entropy. And in fact, the saddle point configuration they are asking for, they say certain saddle points arise because of topology change, allowing topology change in the gravity theory. The CGHS model didn't do, but no, if you allow the topology change, you actually don't get those saddles. So we actually explained that these were the two errors. So in fact, the argument for the page curve are actually not correct. There were also papers saying that the effective theory like JT gravity, they just gave them arbitrary rules and saying it's an effective theory, I can give it any rules I want, but in fact, there's no rules, as I mentioned earlier in the talk. They don't actually, once you define the effective variables from the exact variables, even if you don't give that particular description, it forces your Lagrangian and forces your quantities in the effective theory, so you cannot choose them arbitrarily. And the ones they have chosen, well, for them in the exact theory, you cannot actually get the page curve to come down. I also put something here in black because a different class of papers, many of the papers actually just have a circular argument. They're not saying anything about the black hole, simply model a piece of coal, and they just have radiation coming from a piece of coal, and several things to do with papers we've been talking a lot about information and page curves and so on. They're just modeling a piece of coal without a smooth horizon and saying the page curve comes down, but of course that's completely empty. If you have a piece of coal, of course the page curve will come down. Okay, so just to summarize what I've said so far, the information problem has been solved several years ago by fuzzballs, and all the wormhole stuff is incorrect. So should we just say that, okay, it's over, people are doing nonsense, let them keep doing nonsense, the paradox is solved, we should go on to do something else? Why is the resolution of the information paradox, the fact the answer is fuzzballs and not any of these other things like wormholes, why is it relevant? And actually it's very relevant, because what we have learned from the whole fuzzball thing is that the size of a bound state actually grows with the number of quanta in the bound state. It's not Planck scale, it actually grows in a certain way, and tunneling into these large number of fuzzball states, this is where the Beckstein entropy becomes important. It actually, this entropy-enhanced tunneling violates semi-classical dynamics at a macroscopic length scale. So this is the real lesson that we have learned from everything. The entropy-enhanced tunneling actually leads to a second mode of failure of the semi-classical approximation. We always knew semi-classical approximation fails when curvatures get to the Planck length scale. But that's not happening at the black hole horizon. But the point is, if you have a large number of quanta n, then there's a second failure of the semi-classical approximation induced by tunneling into the large number of fuzzball states, which happens at a distance which is proportional to the number of quanta involved in the state, and happens at the scale of the black hole horizon. It's the second mode of failure of the semi-classical approximation that is the real lesson that we have learned from all this. And so with that solution, what we should really be doing is going on to understand what happens at the Big Bang, because the real interesting question now is that the black hole singularity, where everything falls in and crushes to a point, is very much like the singularity in a time reverse sense to what happened at the Big Bang, where everything also went and crushed down to a point. And all these other nonsense about wormholes and so on is simply taking us away from actually addressing the real questions which our field should be addressing right now in our field. So what lesson can we extract from the fuzzball paradigm for the Big Bang? If the microstates are fuzzballs, then we, of course, have no trouble with the information paradox because information just comes out. But what we should really ask, here's the question we can ask further: how exactly does a collapsing shell tunnel itself into a fuzzball? Now, in principle, we know the answer to this, because if all the states, the time-independent states, which we have found, we have constructed, let's call them Fi, any other state which is dynamical and evolving in time, like this wave function of the shell which is falling in, is a linear superposition of these time-independent eigenstates. And then if we actually, there should be an I here. If we then evolve these states with time, we will find the evolution of this and what it actually does. So once you've found the time-independent states of any quantum theory, of course, you know all the evolution. But in practice, of course, we don't know how to take all these states, superpose them, evolve them. That's going to be impossible. So knowing what we know about fuzzballs, can we give at least a qualitative answer to what really broke the semi-classical approximation in a dynamical sense? So more precisely, we can force the question like this. And I think it's very interesting to ask the question in this way, because it shows us the path into where we should go with what we have learned from fuzzballs. So suppose you try to make a black hole with, let's say, 4 particles, each of mass m/4, coming in radially at the speed of light. Well then, no particle knows the other particle is coming, because you can check that the light signal from any of these particles actually cannot reach the other particle. Okay, so then if no particle knows the other guy is coming by itself, it will just keep going. It will feel nothing special as it crosses this particular radius, r equals 2m, where they all get trapped in the horizon. And after that, the light cones turn inwards. So even though when the particles meet in the center, now they know the other guy was coming in, whatever they do there and the stringy mess they produce, well, the light cones are turned inwards, so it can't go out and influence the horizon, at least if causality were true. And if it can't influence the horizon remains as it is, then you will get back your pair creation. You're back in the information paradox. So what actually happens here, how do we avoid getting trapped? Here's the same thing in different language. If you take a star which is collapsing, the light cones outside, of course, point, can go out, you can go in. But as you go inside the closed trapped surface, this is the closed trapped surface, the horizon radius, the light cones point purely in, and you go to the center. But once you're here, this is space-like for you, so you can't actually affect this region. Okay, so how does a fuzzball form? Which of these steps is wrong? Well, there are 3 possibilities. One is that causality is actually violated in low energy, in low regions of low curvature. And these particles did know the other guys were coming. Okay, and so then maybe they did something, and as they reached the horizon, something happened, and maybe a fuzzball formed, and you didn't actually get the guys going to the horizon. Or maybe when the singularity forms, then they know about each other. Before that, they did not. But because something very singular has happened, the normal rules of quantum gravity break, and you can even go to the regions of gently curved space in an acausal fashion, like from here out to here, it's acausal, and this is a gently curved space, but maybe you can still get there somehow and modify the horizon and then make the fuzzball. Or perhaps string theory is completely local, completely causal, you can't break the light cone, and still somehow it is able to sense the formation of a closed trapped surface and respond in such a way that the fuzzballs form and no causality is violated at any stage. Okay, actually, with all the thinking I put into this problem, I haven't been able to find any violation of causality which will allow A and B to happen in string theory. But we did find an automatic way in which C can happen, and that's what we call the vector hypothesis. And I'll just maybe take 5 minutes to say a little bit about that and then stop. So the idea of this is the following. In a quantum field theory, the vacuum has virtual fluctuations of elementary particles. So if you take the vacuum in this room, it doesn't have any electrons or positrons, but as we know, there are virtual fluctuations of these, for example, the ones that are important in Hawking radiation. But you could ask a further question. If a bound state of E plus and E minus exists like a positronium, are there vacuum fluctuations corresponding to a tight bound state like a positronium? If you think for a second, you'll realize the answer is yes. There'll be positroniums also in the vacuum. There'll be mesons like quark, anti-quark. And if you do the quantum fluctuations of scalar field representing the mesons, yes, you'll find fluctuations of mesons. Well, what about more complicated bound states like a benzene ring? It's also just made out of the same objects in QED. Could you have a virtual fluctuation corresponding to a whole benzene ring coming out? You'd be forced to say the answer is yes. The probability is very low because it's fairly heavy, like 6 atomic weights. In string theory, the fuzzballs are just bound states to the fundamental objects. So just like you can have virtual fluctuations of gravitons or strings, you can also have virtual fluctuations of fuzzball type configurations, and the virtual ones are just representing these kind of gray bubbles. And of course, the fluctuation to any large fuzzball configuration will be highly suppressed, and you can estimate the suppression. But again, because there are a very large number of fuzzball configurations, there'll be a corresponding enhancement because there's some amplitude for at least one of those to be excited in each region of space. So the picture of the quantum gravity vacuum actually looks like this. There are like these virtual fuzzballs of all sizes around every point floating around, and that's the vacuums. These are not on-shell fuzzballs. My total energy right now is 0. And you can see the picture now looks a lot like the picture of the vacuum of the ground state at a second order phase transition. So this, I think, is a lesson we should extract from the fuzzball paradigm, that normally we think of like if you're not at the critical point in a condensed matter system, your fluctuations in an Ising model, for example, will just be the level of a single spin. It may go up or down. That's analogous to saying that the fluctuation in the quantum gravity vacuum is just at the level of the Planck scale. Something happens at the microscopic scale. But no, the vacuum is actually quite different. And I will argue that if the vacuum doesn't have the second order phase transition structure, you cannot solve the information puzzle without violating causality at low curvature. So here you will actually have these bubbles of all sizes forming, just like there are bubbles of all sizes in the Ising model as you reach the critical point. Okay, but this is all still just the vacuum, and that's the nature of the vacuum. And if you ask for some property of these virtual configurations, we know how to make them by looking at the kind of work that many of you have been doing. And if you look at that, you will find that these fuzzball configurations, if you take any one of them, try to stretch it or compress it, it costs you energy. They don't want to stretch or compress, so we call them compression resistant. And you can just model that by saying that if you take some virtual fluctuation of radius RV, V here is for virtual, and you compress it by its own order of magnitude of the radius, it costs you an extra energy, which is of the order of the mass of a black hole of this radius. Okay, so that you just extract from what you know about fuzzballs, and just it's a scale anyway. It's a natural scale in the problem. Okay, so here's a quantitative picture of the quantum gravity vacuum, and because these are virtual, extended in size, compression-resistant objects, we just use these initials to just call them vectors for short. Well, what's the effect of this quantum gravity vacuum? Well, here's the virtual fluctuation, and suppose there's a star sitting in there. The gravitational potential of the star tries to squeeze the vector inside. For example, there's a benzene ring virtual fluctuation here. In this potential, it would be squeezed to a slightly smaller configuration. But of course, it doesn't want to crush because the benzene ring has a certain size. It will squeeze a little bit and then stabilize, which is exactly what the vector does as well. And all this dynamics of the vacuum, readjusting its vacuum polarization, which is basically what these things are, is all included in the low energy Einstein dynamics, which is R root minus G. But now see what happens when there is a closed trap surface. This is for the traditional picture of black hole formation. With the formation of a closed trap surface, the light cones point inwards here. And so a virtual fluctuation which was in the vacuum already present, but which is inside the closed trap surface, now it has no choice but to keep monotonically compressing. It can't actually stabilize because the light cones point inwards. And so it gets squeezed, and ultimately these structures which I had drawn break. And the process of squeezing then actually leads to converting the virtual fluctuation into an all-shell fluctuation. So in some sense, this is what happened in Hawking radiation at a much simpler level. The virtual fluctuations of E plus E minus pairs, if you change the potential too much, then the vacuum doesn't automatically go to the new vacuum. It just leads to creating on-shell pairs. And here this monotonic squeezing of these, which happens when there's a closed trap surface, they can't readjust to squeeze a little bit and stabilize the way I do it here for a star. If you form a closed trap surface, they must keep squeezing, the wave function deformed by order 1, and they become on-shell vectors, and then that's how the fuzzball actually nucleates. So you can see how there's no violation of causality at any stage. No signals propagate outside the light cone at any stage. The fact the vacuum already had these extended fluctuations, and that's not a violation of causality, just like benzene ring fluctuations that exist in this room. But that's because even though the benzene ring is 6 angstroms in size, the room has been here for a time much longer than the light crossing time for 6 angstroms. So if making the benzene rings lowers the energy of that particular state, there will be those virtual fluctuations in the vacuum. Well, then if these vectors exist in the vacuum, because they're extended in size, they can respond to the formation of a closed trap surface. Exactly how they do that is in this paper where we talk a little more detail about vectors.
Just a sec. We're coming well over the hour at this point, so we should finish and go to questions soon.
Yes, this is almost my last slide. So the vectors here have an interesting implication for cosmology. And in cosmology, then what would happen is, in black holes, we said that if something is inside the horizon, it keeps compressing just because structure of light cones. But if you go to an expanding cosmology, you in fact find anti-trap surfaces where vectors must keep expanding. So just the way vectors got crushed here and created the fuzzballs, the dynamics of the same vectors in cosmology, which leads to their stretching, actually creates an extra energy, which gives extra energy. And if you check the scales, it's at the scale of the closure energy density of the universe. In these papers, we explored this possibility, and we found that this energy we get from the stretching of vectors, the same thing that solved the information puzzle for us, can perhaps provide the energy required to drive inflation. It may provide a dark energy today. It may also explain the discrepancy between the Hubble constant values, between the CMB and low redshaped objects, because we always find extra energy gets pushed in when you actually change the power law of evolution. So when the power law changes from something to something else, like from the radiation to dust, that's when you actually get this extra energy which is induced. And in fact, people have argued that exactly that epoch you need extra energy to explain this discrepancy in redshifts. Okay, so this is my summary slide. The information paradox has been comprehensively solved in string theory by the fuzzball paradigm. So we shouldn't keep saying one does not quite know the resolution of the information paradox. It's vital to explore the structure and dynamics of fuzzballs, which all of you are doing, because that's, I think, the path forward with what we have been doing with string theory. And the effective small correction theorem tells us that all the other attempts to maintain a smooth horizon, well, they cannot succeed. And that's why all the wormhole paradigm models that are into inconsistencies. And it's important to understand the dynamics of fuzzball formation, because that may help us to resolve the fundamental puzzles of cosmology. So thank you very much, and I'll stop there.
Can you hear me, Samir? No. Okay. It looks like can you hear me?
I can hear you.
Good. Okay. The sounds was turned on. Questions?
Can you hear me?
Yes.
Okay. I have two questions about non-locality. Oh, this sounds terrible.
So I can't hear you right now.
Hello? Yeah.
Okay, I could hear again, but there was an echo.
Try, hello?
That's better. That works.
Okay. You can hear me?
Yes.
Okay, good. So I have two questions about non-locality, so I'll ask them together. My first is, I like this Fekro picture of formation, right? So it's sort of a way to get around, let's say, both collapse, but also non-locality. So let's say this is the microscopic theory. Then if you, in some way that, we don't know how to do, if we would integrate out the microscopics and go to some kind of a coarse grain theory, wouldn't you agree that the coarse grain theory has to have some kind of an effective non-locality in it, because it's exactly these let's say virtual fuzzballs appearing that you're integrating out, and then you get some kind of an effective non-local effective theory. That would be my first question about non-locality. And then second, okay, there's a lot of these different paradigms and ideas about, and so you've clearly thought about them more than I want to, but there's also one paradigm from Papadopoulos and Raju, which I think is very, very well thought out, where you do see non-localities again in some kind of an effective field theory description. You do see little non-localities appearing, and there it's sort of understood how you should deal with them, how you should view them as, this is something very small, so you don't see them if you're just looking at coarse grain semi-classical observables, but nevertheless they are there, and in a microscopic theory they play an important part in resolving let's say the information paradox issues. And this is in holography, so it's sort of well understood how this works. So could you maybe comment on these two things of non-locality, which I think you would not agree with, that these should be there? Yeah,
let me see if I can say something about each of these points. So First of all, it's very important that the exact theory not have a non-locality, because in exact string theory, with whatever I've ever tried to play with, deep brains diagrams, very complicated things, there has been never any leakage outside the light code. So and I think you are good with that too. Now let's talk about trying to make a semi-classical or some effective theory out of that. Now that even in QED, because the vacuum contains, let's say, benzene rings fluctuations or mesonic fluctuations, if you try to integrate out the mesons, you will get an effective theory which may have a Lagrangian, which is non-local across the size of a meson, right? That is, so you may try to make such an effective theory out of this. I don't actually know how to make one, but there are two issues that you have to be careful about. Firstly, the moment you try to make an effective theory of that way, where you integrate out the fuzzballs, you will also lose in that effective theory any way to address Hawking radiation. So you cannot even try to answer the issue of the information paradox, right? Because Hawking radiation is very delicate at the level of one fluctuation. So you have to be careful you don't lose the baby with the bathwater. And I think that's a little bit of what has happened with what these people have been trying to do. They've been trying to say, okay, 2D gravity is an effective theory, which I can describe the physics. And look, I can now say something about Hawking radiation. But the reason they ran into trouble is you cannot actually then say anything about Hawking radiation. And in fact, the fact that the 2D effective theory breaks down inside the horizon, you lose that as well. But the more important,
Samir, I think Daniel wants to find the effective theory to use it to compute multiple moments and other things. I mean, he just wants to understand the microscopic effect of the effective theory. He doesn't care about the information loss.
Okay. So I was just answering the question about the information loss. Maybe just me say one more thing about it. The kind of non-locality that many of these people are talking about is something which is a non-locality between the black hole and infinity. That's what they need to get their page curve to come down. And with the effective theory you're talking about, you can absolutely make effective theories inside the region, let's say 2M or 4M, and you can get effective non-localities there. That's fine, depending on how you make that theory. And if you're not trying to ask Hawking radiation questions, that may be fine as well. But let's just distinguish that from non-locality which connect the black hole to infinity, because that's what these people are using to make the page curve comes down. And that's the non-locality I was talking about. That's also the kind of non-locality that people like Raju are having. So I have spent quite a bit of time in the Papademos Raju papers, and actually I do not find that they make any sense. So I've also talked to Raju about it a few months ago and also at other times in the past. And in the end, what they are saying amounts to the following. In fact, these are the very words they use. They're saying in any theory with gravity doesn't require black holes, doesn't require any strong non-perturbative quantum gravity effect, even in weak gravity. It's an operational fact they're claiming that by doing an experiment on a big, let's say, sphere out of, let's say, 1,000,000 mile radius, they can flip a spin sitting in the middle acausally. Okay, so they'll do some measurement at infinity and they'll flip the spin. And the argument they use for that are actually incorrect. I've written a SciPost article showing where the error is. So, and we can discuss that to show where the error is, but the answer is not correct. And it looks reasonable when they try to say, but this kind of acausality, you cannot argue that by just putting in, there's no input from gravity. It's just the fact that you have gravity and you have the constraint in gravity. They have the confusion how they use the gravity constraint. So they are not understanding the gravity constraint correctly. And from that, they are concluding that they can actually make a measurement at infinity and flip a spin inside. We know that you cannot actually do things like that. It's just a mistake with understanding ER equals EPR. And I think it's the same mistake.
Hopefully we won't get horrible feedback. Can you hear me, Samir?
Yes.
Yeah. Okay. So I had a question. You've went rushing over why JT gravity is bad, but I wanted to understand, because we had some very nice talks on JT gravity here, where they appeared to be counting exactly the kind of microstates that we care about and we care to be counting. So this is obviously a coarse-grained Euclidean theory, which if you universalize or capture some universal density of states. So that's not inconsistent. So what is your objection to JT gravity? It's just that it can't reveal the microstates, but it does seem to be able to count them.
Oh, absolutely. So I think this is exactly the kind of thing that Sen has been doing with, in his program with computing the partition functions of extremal holes, right? So the point is, you can always, this is just all an extension of Gibbons Hawking, right? So the actual microstates are fuzzballs. If you put them go to Euclidean theory and put them in a thermal loop, and then you can write the entire path integral for that, and that will give you the entropy. That's always standardly true for any theory. And then if that one loop path integral has a saddle point, and you expand in different orders about a saddle point, you will get the entropy. So now you can do the Gibbons-Hawking to more orders, which is what for the extremal case Sen was doing. And I actually heard the talk here about the JT gravity. That's what Baldacina and the speaker and so on have been doing with JT gravity to other orders. And it may well be correct. So if you have a theory of gravity, which has extracted the right things, which would to be the low energy theory of string theory, you would of course get the correct partition function. The actual state that they are counting, they have to realize are fuzzball states. And if they continue the Euclidean saddle point analytically to get the Lorentzian black hole, that is the mistake.
Just another question also from me. So after our review, it became very clear that there are a lot of people in this other community who were embracing long-range non-locality in quantum field theory as a resolution of this. I mean, it's certainly a place I don't want to go, dealing with the whack-a-mole of answering all these mechanisms for long-range, subtle, complex, but long-range order M cubed non-localities. So is there a simpler way of going after these arguments, or you sent me this wonderful shopping list, but is there something simple you can say about why these are obviously wrong if you meet somebody who embraces long-range non-locality?
Yeah, I think the first thing we should ask such a person is, forget black holes, because that's why they are saying all these things. But if we just take two spins very far from each other, what does the non-locality do for them? Does it mean that if I flip one spin, there's an actual Hamiltonian interaction on the other spin? Does it fall off with distance? Does it mean the two spins are not independent in some way? And you will find right at that step, the moment you start asking these questions, whatever they are answering will degenerate into nonsense. But depending on which way it degenerates into nonsense, you will see where the errors are. So sometimes they would say these two spins are not independent. Then you ask, okay, just slow down. What does it mean? This spin had a two-dimensional Hilbert space. This had a two-dimensional Hilbert space. I had four-dimensional Hilbert space in my naive thinking. What does it mean to say they're not independent? This is the most common thing you hear from these people. And they would say, so you ask them, does it mean they have 3.9 dimensional Hilbert space? They say, no, of course, that's not true. So you say, does it mean if I flip one spin, the other one flips? Maybe they'll say yes, maybe they'll say no. If they say yes, you say, okay, if I increase the distance, will they still flip? And they may say, okay, the effect will go down. So you say, okay, you're looking for a long distance interaction. Is that all you're saying? There's a long distance interaction. Okay, what scale does it fall off with? The only scale in the problem is Planck length. So does it fall off like with Planck length? In that case, all the effects are too small to help you with the information paradox. Go back and use the small correction theorem. So, well, if you just keep asking them what do they mean by the non-locality, it will all become clear. But the place where most of these arguments are hiding is they say, look, everything is actually holographic. The exact bits are at infinity. When you try to make the actual bits in space-time, they are approximate. So the spin over here is made out of the same degrees of freedom as the spins over here. They're slightly overlapping, so they're not independent. But if you go back and ask what that means in terms of two spins in Minkowski space very far away, you will soon find it actually doesn't mean anything. They'll actually have to come back and say the spins are independent and do exactly what you expect in the lab. At the moment they do that, you take that answer, transport it back to what happened in the Hawking radiation problem, where you can take the spins as far from the hole as you want and then measure them. All the radiation has come out. You can take all the radiation has come out. Each quantum can be taken as far from it as you want and measure at leisure. And you ask them, what are you saying? And there'll be nothing there. So I think it's best to actually find somebody who believes in that and just have a full-scale discussion. If there was somebody like that at the conference, we can happily have a discussion with that. But because it goes in so many different directions, some of that we have tried to actually talk about in this November review, but different people just say different things.
Any other questions? Oh, Ibu, hang on.
my question is, so you gave a long discussion on where errors might be appearing in these arguments. There is another sort of perspective, which I was hoping you can comment on. One way to at least to see how the Hawking page might turn around is to understand that at late times you can have new saddles that dominate the Euclidean path integral, and those new saddles, when accounted for appropriately, would actually turn the page, the Hawking page, sorry, the page curve around. And I guess such an idea can be more broadly realized in different ways. Would you comment on that?
Yeah, so I spent quite some time on those saddle point papers, and I actually found none of the arguments to be correct. And in fact, we have spent 2 sections of this November paper actually explaining all the mistakes. And they're wrong in multiple ways, and at least the 2 of the central ways that they are wrong are like this. So the mistakes are in the following way. You're trying to compute the entanglement of something with something. Okay, let's start there. There is actually no path integral you can set up to compute the entanglement that they're actually trying to compute in the way that they are trying to compute it. Because look at what they are doing. In an entanglement, there's a set inside, let's call it A, and a set outside, which is B, which is the radiation. You want an entanglement of A with B, right? Then they will say, they will do something, they will close it, they'll finally get to some saddle point and say, okay, here's my manifold. If you look at the manifold they have, it actually has no boundaries. It just looks like a cigar. This looks like 2 cigars. Right? Suppose you try to compute a second Renyi entropy. It doesn't have any boundary. If it doesn't have any boundary, where do you input the state whose entanglement you are computing? So there is a way to compute entanglement entropy of 2 segments of a 2D CFT, right, with each other by using a path integral. But that always has this particular thing as a cut. Okay, so you can compute for any one state. The state for which they actually want to compute, you can't actually set up a path integral for that state. So if you keep going up and seeing where are they saying that this is the path integral they want to compute, you find what they are computing the action for, the path integral they write down is not the one which gives you the entanglement entropy you want. So they actually start going the Renyi entropy way. Let's just say you want to compute a second Renyi entropy R2. What you're computing, that would be, you have to compute trace of rho square. But they're not computing that. They first replace it by a different quantity, which is trace of rho square plus trace of rho whole squared. Now it's not the Renyi entropy anymore. Then what they say is, if you go to late times, they find the second piece, which they added for incorrectly, trace of rho whole squared dominates over the first piece. Now if you go, so then they take that and they throw away the piece trace of rho squared, which was the actual Renyi entropy. And then if you ask what is trace of rho whole square, the piece which is dominating, if you take it, what is it? Well, trace of rho actually gives the Gibbons-Hawking entropy. So the whole thing is completely nonsensical. You're not computing the Renyi entropy, which will actually give you the entanglement. You add to it a piece, which is actually going to give you the Gibbons-Hawking entropy. At late times, that piece dominates, and you say, I got the Gibbons-Hawking entropy. Look, I got the entropy of the black hole. And then you ask, why did you add this extra piece, the one which replaced trace rho square with trace rho square plus trace of rho whole square? And then they say, look, if I connect my slices in a different way, all topologies are allowed. So it's a topology thing. And what the old pictures did in the Gibbons-Hawking and CGHS model, they never took topology change into account. Well, you go back and put topology change in the 1+1 gravity or any other gravity theory, and it doesn't give you those additional pieces in the Renyi entropy. So it just looks like a game where people have just taken whatever they felt like and put wherever they felt like. But if you go back and look at first principles, what is the path integral which will give you the Renyi entropy? It's not this one. If you take the path integral, you say what's actually computing, it's actually computing Gibbons-Hawking, which we know will always give you the area. And if you then go and ask, does this one have a saddle? It doesn't have a saddle. So you can go and look at those, the way we spent 2 different sections of the paper doing this, but the errors are in all these places. And there's actually no argument you can make using 2D gravity that the page curve of the full theory will come down. And the simplest way to see that is the same 2D gravity, which has a CGHS model. The page curve, you can explicitly compute the page curve and it goes up. And then the only thing to say about that is that you haven't taken topology change into account, but you can easily do that. The 1+1 differential gravity, all that happens, the line can just break into multiple pieces and the page curve still goes up. So it just doesn't make any sense.
Yeah, I think so.
I had a more practical question. I don't know if people here in the room also.
Yes.
So I had a more practical question. Samir, you were saying that, and I think it's also following on Daniel's question about the effective action. So, okay, let's say, we had all these talks by people who do, LIGO and, measurements of gravity waves. And, those guys are like, okay, great, you guys have quantum tunneling, you guys have all these geometries, but, if I'm to get something to get my LIGO or like, Lisa curves, if I expect anything to be different from the black hole, the question is, how can I parameterize it? And in particular, if I integrate out all these fuzzball degrees of freedom, all these E2 degrees of freedom, I expect to get some sort of effective action. Again, this is Nick has this principle that when you have a lot of things, everything, there's always some semi-classical limit. So there should be some sort of effective action which actually can allow me to capture the global dynamics of these big fat balls of fuzz as opposed to as opposed to say a curved black hole. Now, what I understood from your talk, Samir, and which makes a lot of sense, is that this action would be non-local. So you don't expect the action to be just some local T mu nu which you put at the scale of the horizon, which you put in the ball, and again a local action also satisfying various energy conditions doesn't stick at the horizon size. So it should be some sort of non-local action. The question is can we cook up such an action? Can we, because again people are asking us desperately give us something, give us a signal for can we cook up something which is string theory inspired, which which captures these dynamics?
Yeah, so let me give you two different comments on that answer. So we just put out a gravity essay this year that Ben is talking about at this workshop, right? About the gravity wave possibility that when you have a gravity wave emission from black hole merger, will you actually get a echo?
Yeah, but echoes, I mean, I don't think anybody took them seriously. I mean, okay, echoes are more like a publicity stunt by people, again, I'm on YouTube, so I'm saying that loudly. I mean, more like, for example, if you look at multiple moments of Kerr, when you spin a ball of dust, or when you spin a ball of liquid, or when you spin a ball of metal, then, you get different multiple moments than Kerr. To get exactly the Kerr multiple moments, you need to spin, a completely fine-tuned disk, which is, so there's an infinite fine-tuning involved in getting exactly the Kerr multiples. And the question is, if I'm to spin, a ball of fuzz, why would I get the Kerr multiples? I would expect to get something else. And the question is, can I have a model? Can we build even some non-local model? I don't care. Any model which I can give to some people who compute, multiple moments, and to obtain some sort of, deviations from Kerr coming from this structure, coming from these vectors, and coming from the microstates.
So I'm not exactly answering the question which you just asked. I mean, all I was saying about the gravity wave reflection is that what happens is that, again, with this picture just put back up on the slide, initially, it's in a time dependent situation, at least when you initially try to make a horizon, causality tells you that you will make one, and then the virtual fluctuations respond to fill in that vacuum with real excitations, right? So this is what we, starting with first place, is what we understand how fuzzballs behave. Now, if you're in a time independent situation where a curved black hole has been there for a while, I understand this is not relevant. This is the dynamics part of it. So the only place where I know right now how to actually try to do some dynamics with these fuzzballs is what I was saying here about the cosmology, that here because of dynamical situation, the vectors are actually, virtual fluctuations are actually being stretched. And so we are trying to, in fact, do that right now. We're trying to write an effective action for these vectors, right? Because stretching them, as we said, costs energy, this kind of energy. And so if you just make an effective action for that, we just a model, right? You put a parameter for how much energy for how much stretching, then that will tell you that if you stretch, if the cosmology is stretching and expanding at a certain rate, you may get a lambda, a cosmical constant of a corresponding value, some fraction of the closure density. So in that way, I think it's easy to, well, not easy, but there are a few parameters with which you can model the thing here. And just like modeling it by elastic sheets, right? You just have elastic which spreads, which stretches and compresses. So you put that in, because that's exactly what solves the black hole puzzle here. So if you just put it, instead of compression, put an expansion, it gives you extra energy at different epochs in cosmology. And then with this model, you can try to see whether you can fit 1, inflation, 2, dark energy today, and 3, this transition extra energy that you need when you, because of mismatch of the Hubble constant. So, so I think there are at least 3 possible different places where to fit data from basically one equation of state. And I think that's something which I find interesting.
Thanks.
Can you say again, sorry? Yeah. Okay, so we have no more questions from the room. So let's wrap up the session. And let's thank Samir and everybody for comments and questions. Let's thank Samir for a very nice talk again.
Thank you.